So perhaps information is encoded on the event horizon as a hologram. We don't know yet. But this is all about how not to destroy information. And we are going to be talking about how not to destroy information in our system. So how many people write software systems? Should have quite a few people who write software systems. Do you write systems using a relational database? All right. Do you use update statements? Okay. Do you use delete statements? All right. Well, I'm afraid to tell you, you've been destroying information. So let's see how we can not destroy data. So the typical application that we build is a CRUD application. So create, read, update, delete. And you can map these 4 operations one-to-one onto the 4 SQL commands: insert, select, update, delete. So if you're reading information, that's a select statement. Reading information isn't going to destroy anything. That's perfectly safe. Inserting information, that's not going to destroy what's already there. It's just adding new information to the system. So there are 2 operations that actually do destroy data. So obviously delete is destructive. In fact, I don't like to call it delete. I want you to know what you're doing. You are purging information from the system. It no longer exists. So I like to call it create, read, update, and purge. But actually, update is destructive as well, because the information that was in that row is no longer there. So you're overwriting it. Or I like to use the term alter. So you're altering the data that was there. It's not updating. Hey, it was out of date. Now it's fresh. And update's a great thing. No, this is altering data. So rather than CRUD, create, read, update, delete, I think this is a bit more realistic acronym for what we do with our system. So we have some alternatives, some options for how we can build systems that don't use create, read, update, delete, but preserve information over time. So I want to start by going over 3 of those options, and then we'll dive a bit more deeply into one of them. So we are going to start with the good old audit log. So if I were to create a database that is speakers and sessions at Houston TechFest, unfortunately Harold is not going to be here today, but if he were, he would be doing a talk called "You Really Can Write Code Once and Run It Anywhere." And then Jane Prusakova, also, sorry, not here today, but she would be talking about privacy in the digital age, can you keep a secret? And so we've got these speakers in one table, and the sessions that they're presenting in another table, and we've got foreign key relationship, so we know who's presenting what session. And so here's me, I'll be presenting black holes are cool. But this data is going to change over time. And so we want to keep an audit log. We want to know when things have changed. So, wait a minute, somebody put my name in wrong. If you just search for Michael Perry, you'll get like the children's book author, the world's smallest giant, a whole bunch of really great people named Michael Perry, but it's not me, Michael L. Perry. That's me, so I needed to update that. And so I inserted into the audit log, hey, speaker number 3, I changed the name to insert the L. Okay, and then Harold came along and said, well, I can't really say that you can run it anywhere, but you can run it almost anywhere. So we insert into the audit log, okay, session 12, we changed the title from run it anywhere to run it almost anywhere, and we captured that change in time. And then black holes are cool. Well, we really don't want to do a physics talk, so okay, how not to destroy data, fine. So completely change the title. Now, this is a pretty typical way of recording changes to your relational database over time. But it has some problems. So who can identify what some of the possible problems would be?
You're duplicating the data because you have the old and the new every time.
Yeah, you're duplicating the data, yes. If I were to change it from how not to destroy data to information paradox, then I would have how not to destroy data in there twice. Is it from and as a to? Yeah. And it's also duplicated from the state into the history. Yeah. Any other problems you might see with this? What if one of the columns was an integer? In my audit log, these are strings. I'd have to take that integer and code it as a string. So it's not really honoring the type system. In fact, even with this example, maybe the speaker name is max length of 100 and the session title is max length of 300. So in the audit log, what's the correct data type to use? I don't know, unbounded text. You have to use something extremely generic in order to capture the audit log. So it's got some problems. One of those problems are, it's got a good feature in that it's simple. I can show this to people and say, yeah, that's exactly what I would do. But it's not type safe. So I'm not capturing the data type of the original table. I'm converting everything into a string, and it gets kind of weird. It is also not reliable. So if you think about this, in order to make this work, you have to update your static tables, the tables that are containing your state, and you have to insert into your audit log. And you have to make sure you do both of those at the same time. Can you trust that the audit log got updated? Can you trust that there's a new record in the audit log? If you're not relying upon it to actually run your application logic, how do you know? How do you know? How do you prove it? So it's not actually reliable. So there's another idea out there called event sourcing that attempts to solve these problems. And so with event sourcing, instead of keeping the state of the system and then having an audit log that shows how that state changed, we are keeping all of the changes themselves in an event stream. And then by replaying the stream, we're figuring out what's the current state of the system should be. So if I have an event called speaker created, then I'll say, okay, the speaker ID is 3, their name is Michael Perry, it was created on this particular date. And so I captured that event just as a document. Then more time passes, and then there's a session created. Oh, this session, we'll give it ID 12. It's related to speaker 1, and title is you can write code once and run it anywhere. And that was created at another time. And so more events happen. The speaker name changes. The session is created, another session is created, another speaker is created. And as these events happen, we capture them in the event stream. And now for me to figure out what is the name of that speaker, I have to go back through the event stream and say, okay, I'm looking for speaker number 3. What's his name? So I'll take all of the events that are related to speaker number 3, and I'll play them against an object, a little speaker object. And so that object has a method that handles an event, updates its own internal state. That's just all in memory. And so I play these events, and now I've got an object that's in the appropriate state. It's finally realized. But I need to check all of this history in order to find the changes to these individual objects. So let's suppose the last thing that happens here is that the session title has changed. Now I've changed it from black holes are cool to the information paradox. And then I do another session title changed again, where I change it from the information paradox to how not to destroy data. What is the actual name of this title? Or, I'm sorry, of this talk? That should be an easy one. You all picked it out. Yeah, how not to destroy data. And you can tell that by going through the history and playing each of the events related to session 18. So that means the order matters. What if the last two happened in the reverse order? You'd end up with a talk called the information paradox. So the order between those two matters. Take a look at these two. I've got the speaker name changed and session created, both related to speaker ID 3. But in one, I changed my name, and in another one, I created a session. And so does the order matter there? They're both related to the same objects, but it doesn't matter which one came first. Sometimes order matters, sometimes it doesn't. And as it turns out, that is an important aspect of modeling software, especially in a distributed system. So event sourcing, it has some great benefits in that it is type safe. We are keeping track of those documents, and we have just the right type of documents in our system. It is reliable because you are relying upon that event stream in order to know the current state of the system. It's not simple. I have to really explain to people how to create an event stream, how to design your events, how to replay them. There's special technology involved in making all of this work. It's not quite as simple as the audit log, but you give that up in exchange for some great benefits. The thing is, that event sourcing is not partially ordered. Sometimes order matters, sometimes order doesn't. The event stream doesn't know which. So you always have one central event stream. This is the system of truth. The events happened in this order, no other order, and you have to be able to go back to that central event stream in order to figure out what's true. Sometimes it matters, and sometimes it doesn't. So that is a big constraint that you're putting on your architecture that sometimes you don't need. So I wanted to talk about a third option, historical modeling, which is partially ordered, and it has the other benefits of event sourcing, in that it's type safe and it's reliable, but it's not simple. So buckle up, we're going to go over something that's a little bit complicated. Historical modeling. Where shall we begin? Let's begin with a relational database. Let's go back to our speaker database. So, our speaker table in that database. So we've got a speaker ID. These speakers, they're going to log into our system, kind of like there's a tool called Lanyard. There's also speaker rate. There's also anyway, there are these tools that speakers can log into in order to upload all of their talks. So we're going to build that kind of a system. So the speakers have a username, they log in, and then they have their own name. Now, if this were my table, then what kind of operation would I have to do in order to change the speaker's name? I would have to do an update. And we already said, updates destroy information. We don't want to destroy information. So in order to not have to update this table, let's go ahead and take name out of it. Well, where did the name go? It went somewhere. We have to preserve that information somewhere. We'll get there in a little bit. So just hold off on that one. So all we have is the speaker ID and the username. The important thing about these two pieces of information is that they are immutable. Once you've logged into the system, you can't change your username. So you're using your email address, you're using the username you came up with, you can't change that. It's immutable. So the username is what we use to identify the speaker. So that's the ID that we use outside of the system. The speaker ID is generated when we did the insert, but the username existed before we actually did the insert. And that's the identity of the speaker. That's what we really want to use to identify that speaker. So we're going to use that as the way that we identify the speaker. That's its identity. The speaker ID is just used internally. So we put a uniqueness constraint on that so that we know that we only have one speaker with that ID. Now let's talk about how we would mention a speaker from outside the system. What's the REST API look like for this thing? So if I want to talk about a speaker from the perspective of this REST API, I don't say speaker ID 3. I say the speaker that has the username Michael L. Perry. That's how I identify speakers. So this is the identity. It's all of the fields besides the primary key. and they're all immutable, so identity can't change. And so that's the thing to start with. Now, let's suppose that I want to add sessions to this database. So I've got my session table, foreign key back to the speaker who's actually speaking. We've got a title. So I want to create a session with this title. Oh, wait a minute. Title is mutable. That can't be in here. Let's move that out. But now I've got just, if I take away the session ID, that's the internal ID, I just have the speaker ID. And if that's supposed to be the identity of this thing, that means that a speaker can only have one session. That doesn't make any sense. So I have to add something else in order to make this unique. So I'll add a timestamp. Could be a good, could be a random number, just something that makes this session unique. And it has to be something that you know before you did the insert. And that's what makes it a reasonable, reliable identity that you can use outside of the system. So we're going to put uniqueness constraints on those two things. So if I've got this particular speaker ID and I've got this particular timestamp, that's talking about this session and no other. So put the uniqueness constraint on those. So that means that the identity of a session is the speaker ID and the timestamp, right? What's wrong with that? The speaker ID and the timestamp. The speaker ID, that's just the internal ID. That can't be the identity. The identity of the speaker is the speaker's username. So the identity of a session is the username and the timestamp. So we're divorcing ourselves from all of the internal automatically generated IDs. So if I wanted to refer to a session from the REST API, I would talk about the session whose speaker has the username Michael L. Perry and the session has the timestamp of this particular time. So now at this point, what I can do is within my client application, I've logged in, so okay, I've got this JSON object that says your username is Michael L. Perry. That's never going to change. And then I say I want to create a new session. Here's my new session button. Hit that button, creates this JSON object. It never had to go back to the server in order to get my speaker ID. It's just information that was known there on the client when I logged in. Yes?
The timestamp, should it have any meaning? Is it like the timestamp that the record was created, or the timestamp that the session will occur, which could potentially change?
Good question. So is it the time that the record was created, or when the session would occur? It should just be the time that the record was created. Right. If it was the time the session will occur, that could happen in the future. It could change. It could never happen at all. This session was not accepted. Well, this session was, but perhaps when I created this object, this record, the session hadn't been accepted yet. And in fact, I might present this session at multiple conferences. So yeah, that timestamp, that would be part of the domain. This one is just created at the time that you hit that button. Yeah. And it's just enough to make it distinct from other sessions by the same speaker. So that is going to be the identity of the session. So the rule is that the rule of identity. Every field is immutable. You don't have any immutable fields at all in these tables. The surrogate key, such as your primary key, the one that's generated when you do an insert, that is only used internally. You never expose that to the outside. And we're going to talk about why that is. But just imagine, what if I wanted to have this system running on a different database? What does that imply? Everything else in your record, all the other immutable fields of the record, are the identity. So that's all you have inside of your record is surrogate key, immutable fields. Those immutable fields are the identity. Okay, so let's continue building our data model here. Let's focus just on sessions. What if you want to delete a session? So we're going to strike updates. We're definitely going to strike deletes. You're not going to delete a session. This is a technique that's often used to delete things a soft delete, right? We just have a deleted flag, and we're going to set the flag in order to make the session deleted.
Tombstone.
What's that?
Tombstone.
A tombstone, yes. That's actually exactly where we're going, is we're going to a tombstone. Yeah, but what's the problem with just the deleted flag being on the record?
Still taking up space.
It's taking up space.
It's mutable.
Right, it's mutable. In order to delete a record, I have to update it. And I don't want to do any updates, because the update deleted to true destroys the information that it used to be false. Well, okay, maybe that's a little bit strict, but that's the rule, no updates. So take away the deleted flag, and instead we've got a session deleted event. So a table that means this particular session was deleted. And so that's the tombstone object that is separate from the one you're deleting.
Well, really, I tend to think of the tombstone as being more like metadata than actual data. So you might get around that little rule of yours.
Oh, I see. Okay. So yeah, tombstone is metadata. It's not the actual data. So by getting around the rule, I think what you're saying is that if you update metadata, you're not destroying the actual data of the system, right? So as we get into the architectural discussions at the end, there are some architectural advantages in treating metadata with this same level of respect of never destroying it. And that comes into play when you're trying to synchronize two databases. So yeah, let's hold that thought for just a second. If instead of the session ID, so here a session deletion would just be, I'm deleting the session whose speaker is Michael Perry and timestamp is this particular time. This is how I would then look for all of the sessions that have not yet been deleted. So we're looking for, select whatever you need from the sessions. Now you're just looking for those sessions where the session ID is not in session deleted. So you could have said with the deleted flag where the session where deleted is false, this would be the equivalent if you're now talking about inserting instead of updating. Okay, so now what if we wanted to be able to restore these sessions over time? Then we would have to have some unique identifier of a particular deletion of a session. So the session ID itself wouldn't be enough to make it distinct. You should be able to delete a session multiple times. And so we add timestamp to session deletion. And so it's exactly the same kind of timestamp as we saw before, where it's the time that was deleted. And now we can identify the session deletion as the session ID and the timestamp. Well, of course, session ID is not the identity of the session. So the session deletion now is the session whose user has the name, Michael Perry, and this timestamp, and the session deletion has that timestamp. So that entire document is immutable, and no matter what internally generated IDs I came up with, that document identifies that particular session deletion.
So you're saying you might store it in the database this way, but you're still considering it an object of the construction below, essentially?
Yes, you're still storing it relationally, but you're considering it as one document. And the identity of that document is everything except for the primary keys. Okay, so now that I've got that, I have the ability to do a restore, and I can say this session restoration is the restoration of a particular session deletion. And now I can only restore a session once by removing its particular deletion. But then if I delete it again, I've got a new deletion, and I can have a restoration that removes that deletion. So this is where I have to start kind of thinking through all of the different, all I can do is insert, but then I need to be able to figure out what's the current state. Is this thing deleted or not? I don't know. Well, it's deleted if there exists a session deletion that does not have a session restoration. And so I can figure out which sessions do actually exist by looking for the ones where the session ID is not in the session deletion, where that session deletion ID is not in session restoration. So you start to build these things on top of each other. So you might be thinking, okay, this is just going to keep on building and building, and you're going to get these really complicated things. In my experience, this is as deep as it ever goes. It goes 2 levels deep. And you often find that that's enough to do the sort of operations that we want to do. We want to be able to delete things and restore them. And then we can delete them again, but that's going back to the second level of that tree. So that is how deletion ends up working in a historical model, is that a fact itself cannot be deleted because that would destroy the information that's in that record. You issue queries where the subsequent deletion does not exist. And then if you need to restore, you need to add a timestamp to the deletion because that's the only way you'll be able to ever delete it again. Now, that gives us a specific example of then a more general pattern that we can start to apply. So for that general pattern, let's start to talk about those mutable properties. So here, I had my speaker with the name. I took the name out. It had to go somewhere. Where did it go? Well, it went into a speaker name table. Makes perfect sense, right? In order to change the name of the speaker, you have to insert what's their new name. Okay, so speaker name, we've got our speaker ID, we've got the name. And now, if I have one speaker record and a whole bunch of speaker name records, what's the current name? What do I actually display on my user interface whenever I display this speaker?
Timestamp.
Timestamp? A timestamp would give us that answer. Timestamp would also be not partially ordered, but it would be totally ordered. I guess I really didn't define partial and full order. But yeah, timestamp, that would be going back to the same challenges of event sourcing. So let's talk about maybe another option. Rather than a timestamp telling us what's the most recent speaker name, what if every time I changed the name, I changed it from something else? So we're looking at the system. I've got a speaker in there, Michael Perry. Then I've got Michael L. Perry's username, the speaker name Michael Perry, and then I insert another speaker name, Michael L. Perry, and I say this changed it from Michael Perry. That was the predecessor. That was the previous version. So to capture that, I've got another table here, speaker name predecessor, that says that was the predecessor. This is the successor. So that was the old version, this is the new version. And I recorded that information just by doing inserts. So if I've got that structure, then I can take a look at that entire set and I can see what is the current name. It's the name that has no successors. Nothing else has claimed it as a predecessor. So that means that in order to identify a particular version of speaker name, I've got the speaker, I've got which name I changed it to, and I've got the list of all of the predecessors. What did it change from? And did I write the query for that? Yes, I did. So, in order to figure out what the current name is, I want to select the name from speaker name, where the speaker ID is, say, 3 in this example, and the speaker name ID is not a predecessor in the speaker name predecessor table. So there's not some future version that claims to have replaced this one.
What if you change it back?
What if you change it back? Excellent question. If I changed it from Michael L. Perry back to Michael Perry, then I would insert another speaker name with just the value Michael Perry, and its predecessor would be the Michael L. Perry version. So I would have this chain. There's actually a system that we might most of us might be familiar with that does this kind of a chaining of different versions of things over time. How many people use Git? Exactly, yeah. So every Git commit, if you look at it inside of something like Git-K, it'll say, what's the parent ID? What's the predecessor commit? And so you can have commits that change your source code to one thing and then back again. But changing it forward is one commit, changing it back is another commit, and they refer back up the chain as parents. So that's precisely how you would model it here. So you're selecting where it's not superseded, there's not a successor. So this is how you would capture mutable properties inside of a historical model. And it's a bit complicated, but this is building on top of the patterns that we saw for things like deletion and for things like identity. So the mutable property itself cannot be part of the fact, because that would require you to do an update. You would want to keep track of which versions came before. So you're always keeping track of your predecessors. These were the versions that you came from. And you query for versions that have no successors, and that gives you the current version. This also allows you to detect and resolve conflicts. So this is where it really comes in, and this is why Git uses this technique. So we talked about having commits that have one parent in order to record I'm making this change from this version going on to the next. Could you ever have a commit that has two parents? So who are my Git folks in the room? Got a few Git folks. And Git is unique in modeling things this way. Other version control systems like TFS don't quite do things this way. But if you wanted to make a change in parallel with somebody else, then you would create a branch. And then when you're finished making your change, you do a merge, precisely. So a merge commit is a Git commit that has two parents. It's saying, okay, I took their changes, I took my changes, I merged them together, and so this one commit supersedes both of them. And so that allows me to resolve conflicts inside of version control. You can do the same thing inside of your applications. Let's suppose you've got a mobile app. You download the information. How many people have used Windows Mobile? I mean, before Windows Phone. Windows Phone is dead. Windows Mobile is dead. So going back to Windows Mobile, there was this thing called ActiveX, or not ActiveX, it was
ActiveSync.
What's that?
ActiveSync.
ActiveSync, yes, perfect. Yes, ActiveSync. It had this wonderful ability of whenever I make changes on my mobile device and it's disconnected, I need to update this person's phone number. Okay, there we go. All done. Now it resyncs. It said, I don't know what just happened. This person has 3 phone numbers. Wait, no. They don't have that phone number anymore. They have this one. It didn't remember that this was a change from that one to this one. It didn't know that predecessor-successor relationship. It just said, well, I was offline and now I'm online and I see 2 versions, so here you go. Or even worse, you delete this contact while you're offline. Go back online, hey, no, delete. So they didn't get this part right, but if they had kept track of their predecessor-successor relationships and kept track of the partial order of these changes, then they would have been able to detect and resolve conflicts even when they were offline. So let's go back to this query real quick. Is there anything else that you can see just from the fact that I'm running this kind of a query? A speaker has one name, right? But this query, it could possibly return more than one name. If it does, what does that mean? What actually happened there?
You changed it.
You changed the name. let's suppose that two different people changed the name. So, so you changed a name from Bob to Robert, and I changed the name from Bob to Bill. We both changed the name from the same predecessor. Neither one of these has the other as a predecessor. So now I have two records, Robert and Bill, neither one of which is a predecessor, neither one of which has a successor, neither one has been superseded. Both of these are equally likely. A conflict has happened, and these are your two candidates. That's what that's telling you. So, running a query in this way, if you get one result, no conflict. You get more than one result, there's been a conflict. These are the possible answers. And so that's how it helps you to detect conflicts. And then in order to resolve them, you just have another version that has both of them as predecessors. You do the merge. So this structure helps you to detect and resolve conflicts. And so that's how you keep track of mutable properties in a historical model. So all of this brings together the various patterns for historical modeling. Let's double check the time. Okay. We're doing okay. Let's take a look. Now, we've got our session. We want to then progress the session through a workflow. So I've submitted this session. And remember, the session's identity is the speaker and the timestamp. So let's suppose that I want to submit this session to a conference. So over here, I've got my conference table. I don't have my conference name because that's immutable. I moved that out of my entity. Instead, I've got my conference GUID. So GUID is a great choice when you're dealing with the top level. I use timestamps for things that deal with a particular property of an entity. So changing the name of somebody over time, or deleting a session over time. Yeah, it's a deletion for that session, so it's already within a smaller scope. Conferences, people can create conferences at various times. Let's suppose that this system gets really popular, and lots of people are creating conferences all at the same time. So a GUID is a great way to be more unique. Anyway, so we've got our conference. It's uniquely identified by the conference GUID. And then I want to submit a session to a conference. I say, okay, I want to present how not to destroy data at Houston TechFest, from Dallas. So I create a submission record. So now I've got two foreign keys, which session, which conference. And then I also have a timestamp. Why? Because over time, I might actually submit this session to this conference more than once. Things might happen, we go back, we go forward. Well, what sort of things might happen? So this session is submitted. Maybe I want to withdraw my submission. Say, oh, nope, never mind. I'm not going to be able to make it. Oh, no, as it turns out, yes, I can make it.
The conference got canceled.
Yeah, exactly.
And rescheduled.
Exactly. So what happens if you cancel a conference and then you reschedule? Oh, resubmit all your talks. So we've got that same sort of deletion pattern happening here, where now the submission can be withdrawn. But because the submission has a timestamp, I can create a new submission for the same talk and the same conference, and it would still be, it would be unique from the previous one. So after a talk has been submitted, I might then accept the talk. So this would then be, Michael, the conference organizer, he would say, yep, I'm going to accept that talk. And he would insert an acceptance for that particular submission with a timestamp, because that acceptance might be withdrawn at some point. But no, you know what, somebody else, they're going to be presenting on that same topic and they're a better speaker than you, so no, you're out. Michael would never do that. So you've got these different activities, these different events that have occurred throughout time. And you might ask the question, well, what is the status of a particular submission? Has this submission been accepted? Has it been withdrawn? Is it still pending? What's the status? So what we would typically do in your CRUD-based application is we would have a status column, and then every time you record some kind of event, you would then also go back and update that status. You would say, okay, the status is now it's submitted, and now the status is it's accepted. But that's an update, and updates destroy data. So instead, if we just insert these events as they occur, then we are keeping track of everything that's happened. We're keeping track of the history of that submission, and we can compute the status. In particular, status is often used in order to answer another question. What's the real question? Well, Michael's asking the question, what talks do I need to review? What talks might I potentially accept? And so he would be looking for those that have been submitted, so in the submitted status. But the real question is, give me all of the submissions that have not yet been accepted. That's the real question he's asking. And we already know how to write that kind of a query. Select submissions where the submission ID is not in acceptance, where acceptance ID is not in acceptance withdrawal. See, we're doing those two layers again. And so we're looking for, okay, if I were to withdraw my acceptance and then I run this query again, hey, there's that submission back again. I can go ahead and accept it again. So the real question isn't what's the status of the submission, it's what's the next action? What can I perform? And so I'm looking for the existence of a thing where I haven't yet performed that action. And so that's what you do in a historical model as opposed to a status in order to keep track of what happened, the history of how it happened, and what's my next step. Yeah, not simple, but really powerful. So, workflow. You never store the status as a mutable property because that would require an update. You also don't use the mutable property pattern in order to satisfy workflow because then you can run into conflicts in terms of status, and what you're really after is what events have happened. So just record those events. So the events move entities through the workflow. So inserting this new event moves the submission to another part of the workflow. And the events always point back to their predecessors. In order to have accepted a talk, it must have been submitted. So the submission ID is a foreign key to the acceptance. In order to have withdrawn an acceptance, it must have accepted it first. So the withdrawn event has a foreign key back to acceptance. And then you always query where the next event does not exist. So my next event, I'm going to accept some talks. So I'm going to query where acceptance does not exist. And that's how you answer workflow questions and keep track of workflow inside of a historical model.
You're going to have a separate table for every event status?
You're going to have a separate table for every event that could occur in the system, yes. So, so then in order to figure out the status of a thing, you look at what events have occurred in this table, join it to that table, where this ID does not exist in that table. And then by the existence or absence of those events, you infer what the status is. Yeah. So, now we get to the really exciting part. What architectural decisions does this enable? One that we already talked about briefly was occasionally connected mobile apps. So let's suppose that you take a snapshot of the data and you put it on a mobile phone, and then when you're offline, you can work with that data. When you go back online, all you've done is you've inserted new records. You haven't updated anything. Inserts merge beautifully. Updates cause problems. So you just take all of the new records that I have and you just send them up to the server. All the new records the server has, and you send them back down to the client. And just like in Git, if you were to do a push or a pull, you're just sharing a bunch of commits that you've already made. Then both sides can say, oh, wait, I see another branch. There's been a conflict. And you can see that conflict on your mobile device, and you can resolve it on your mobile device. And then you can push the resolution back up at some later date. So that's allowed, that's enabled by historical modeling on an occasionally connected mobile app. Think about an occasionally connected mobile app using event sourcing. I know that seeing talks on event sourcing, this has been done, but think about the ramifications of having an event stream that's on the server, that's the single source of truth. And I make a change. I go ahead and insert my event into this event stream. It hasn't made it to the central server yet, so I'm not really 100% confident that it happened in this particular order. There might be something else that superseded it that I just don't know about yet. So then when I do connect, I push all my events up, I pull all the events down, and now I've learned what actually happened. And so things might have happened in a different order than I expected. Other things might be inserted into my event stream. Whereas if you've got partial order, now you're keeping track of the order of events when it matters, but not when it doesn't. So you're not constrained to having a single linear source of truth if you don't need order between two events. So occasionally connected mobile apps using a historical model tend to work better than those that use event sourcing because you can detect, you can resolve conflicts, and you don't keep track of order if you don't need to. Similarly, if you have active-active clusters, this is something that's really difficult to get right inside of an enterprise system. It's like, we want reliability. And so these two geographically distributed databases are going to be serving different areas, and they're both going to be active. And when you make a change here, I'm going to push that change over there, make a change there, I'm going to push it over here, and keep everything in sync. Very difficult to get right. Surprising thing is, once you go to a historical model, it becomes really, really easy. The tools that you get out of the box to do this data synchronization, they love it. They love inserts. They get really confused with updates. And furthermore, if you take the automatically generated ID and that's no longer the identity of the thing, now you can insert in the east, you can insert in the west, they both come up with the same number, that's okay. When they cross, they get opposite numbers, but the identity that you're using is not the inserted identity. It's the it's not your surrogate key. It's a natural key. It's an identity that you came up with when you did the insert. So active-active clusters become much easier when you're using a historical model. Furthermore, microservices, all the rage. So microservices, we give an interface to a whole bunch of different services. What do we typically use for that interface? How do these things talk to the world? HTTP. Yeah, they each have a REST API. And so in order to talk to this microservice, you got to use HTTP, talk to it. HTTP is synchronous. You are going to make a request, then you're going to get the response. You're going to make another request and get the response. And so typically with a microservices architecture, you have services talking to other services using the same API. And so they're also talking synchronously to each other. But what if instead you take this same idea that we've used for synchronizing occasionally connected mobile apps, synchronizing active-active clusters, and now you're synchronizing the different databases of your microservices using these same techniques. And now they're not talking to each other through HTTP anymore. Maybe they're talking to each other through a service bus. This event has occurred. I'll just publish that to the service bus. Hey, I'm interested in that event. Somebody just placed an order. I'm the preferred customer service. So I'm going to subscribe to placed orders. I'm going to insert a whole bunch of stuff into my database. And then now when somebody calls this REST API and says, hey, is this particular person a preferred customer? Then I can just take a look at, hang on, let me take a look at the events that have occurred with that customer. And I can say, yes, based on these events, they're preferred. So it can answer the questions via REST API, but it can synchronize via service bus. And if you use a historical model, then that synchronization becomes really easy. So these are the different architectural decisions, the architectures that are enabled by using historical modeling. If you want to learn more about historical modeling, then you can check out historicalmodeling.com. That's a blog that I put together, different articles about historical modeling, and I'm also putting videos up there. So hopefully this video will go up on historicalmodeling.com as well. The database that we saw here in this example, that is on GitHub, github.com/michaelperry/festify, and that's the TechFest database. And please reach out to me with questions, Michael L. Perry on Twitter. And thank you very much. So any last questions as we wrap up?
How's performance?
How is performance? Right. So as compared to a static database, and I use that term as in it is maintaining state. As compared to that, historical models are slower. They do take more complicated queries in order to answer the same questions. As compared to event sourcing, since with an event store you go through a longer history in order to figure out the status of a thing, a historical model tends to be a little bit better in terms of performance than event sourcing. Also because you can do your historical modeling based on your own local database and you don't have to go to a central event stream. Yeah, good question.
What do you do about eliminating stale data? I mean, you can't keep everything.
Okay, so what do you do with stale data? So yeah, over time you
10 years ago.
yeah, those events don't matter anymore, right? So
You gotta do something with them.
yeah. So what I typically do is I'll build into my data model a clock. So like one good example is to have a data business. So you're doing like a hospitality system, and you're keeping track of tables and checks. You know, people are ordering food at a table. So you've got a data business. Your store opened at this, or your restaurant opened for this date, and then it closed. And that data business is an entity, and so all of the orders relate back to that data business. And now you put a new entity in place, and you're starting to collect orders for that one. Okay, that one goes away. Here's a new data business. So you can archive an entire subset of your tree. So all of the history that happened here, just go ahead and archive that. And then once the data business has passed, it's very likely that you're not going to get another order against that old data business. So given that, you're perfectly safe in taking that, aggregating it, putting it into a data warehouse, and never updating it from that point. So yeah, build a clock into your data model, and it makes that problem a lot easier.
I forget all of my exact database normalization model, but is this effectively like a different form of database normalization?
Is it effectively a different form of database normalization? It is very, if you've gone third normal form,
Yeah.
then you've made a good start. Interesting. I think that
It almost seems like the same kind of exercise.
yeah. It's kind of like it's like another step beyond third. I don't think that. Well, I would have to remember what fourth and fifth are.
Yeah.
Typically don't do fourth and fifth, so I don't remember what they are. But yeah, database normalization does not take away your ability to update and delete, and this definitely does. And it's also beyond the database. It's also what's the REST API look like? The fact that you're never exposing that internal ID outside of your database, which, you know, like I said, opens up a whole world of possibilities, but it's also another constraint. Interesting. I don't know. Thank you again, and enjoy the rest of the conference.
See you later. For solid.
Yes.